9 million people, 170 kilometers of glass, 500 meters of vertical defiance. This is the ultimate war against gravity. This isn't a sci-fi render. It is a $1.5 trillion calculation of tectonic pressure and structural integrity. Imagine a mirror monolith, weighing billions of tons, anchored into the treacherous, shifting sands of the Tabuk Desert. The true battle isn't on the surface. It is the brutal struggle of steel and concrete deep within the earth. To prevent a 500-meter wall from sinking, engineers are driving piles that exceed every known global building standard. Historically, construction steel is forged in distant mills, but for the line, traditional logistics have utterly failed. The sheer scale of 100 million tons of material forced a radical shift. We are building the factories on site. Behold the heart of the project. Massive electric arc furnaces, EAF, operating in the middle of the wasteland. Inside, temperatures scream at 1,600 degrees Celsius to forge ultra-high-strength steel alloys never seen before. AI-driven sensors monitor every pore, ensuring a perfect carbon-to-manganese ratio for extreme corrosion resistance. This specialized alloy must withstand compression forces equivalent to the weight of an entire aircraft carrier fleet. Pouring concrete in a 50-degree-Celsius desert is a physical gamble. The heat is a silent structural killer. Moisture evaporates instantly, causing thermal cracking that could shatter the city's skeletal foundation from within. The solution: liquid nitrogen cooling systems that drop the mixed temperature to a stable 15 degrees Celsius. Assembly engineers monitor the flow in real time, using thermal imaging to guarantee a flawless, monolithic pour. But even the strongest concrete is useless if the ground beneath it shifts. This is where we engage the titans of pressure. We don't use standard pile drivers here. The vibration would destabilize the desert's delicate geological strata. Instead, we deploy massive static hydraulic presses, towering 20 meters high, generating 20,000 tons of raw force. Imagine the weight of 100 blue whales concentrated onto a single steel point. That is the pressure required to anchor the line. These pistons push colossal steel casings through the sand and deep into the bedrock with silent, terrifying precision. Every millimeter of penetration is logged by fiber optic sensors, creating a 3D digital twin of the subterranean support. If the resistance deviates by even a fraction, the assembly engineers halt the process to recalibrate the structural load. Above ground, the skeletal architecture begins to rise a complex lattice of carbon fiber reinforced joints. These joints are the articulated knuckles of the city, designed to flex under extreme thermal expansion. In the desert, materials can expand by centimeters during the day and contract at night. Without flexibility, the city would snap. Precision robots, guided by sub-millimeter GPS, weld these massive nodes with high-energy plasma arcs. Each weld is a masterpiece of metallurgy, undergoing X-ray crystallography to detect microscopic air bubbles. Logistics teams manage a constant stream of over 5,000 heavy lift components arriving at the site every 24 hours. The site is so vast that it requires its own internal high-speed rail network just to move the engineering crews. We are not just building a wall, we are assembling a 500 billion kilogram machine that must breathe and survive. Survival in the desert isn't just about water. It's about managing the violent fluctuations of thermal energy. The mirror facade acts as a double-edged sword, reflecting the sun's glare while trapping heat within its core. To counter this, engineers have integrated a passive lung system, a network of aerodynamic wind chimneys. These shafts use the Venturi effect to pull cool air from the shaded base and vent hot air at the 500-meter summit. But even the air must be engineered. Every cubic meter is scrubbed of desert fine dust using electrostatic filters. This brings us to a critical realization. The line is less of a city and more of a massive, inhabited life support machine. The precision required here is unprecedented. A deviation in the cooling ducts could create localized firestorms. Every joint, every duct, and every glass panel is part of a delicate trillion-dollar equilibrium. And overseeing this equilibrium are teams of specialists who live on the edge of the impossible every single day. The world asks if we can finish it, but the real question is, how do we keep a 170-kilometer machine alive? The answer lies in the spine, the high-speed subterranean artery that dictates the city's pulse. This tunnel is being bored through solid granite using the most advanced TBMs ever manufactured by man. These machines are autonomous leviathans, chewing through 3 meters of rock every hour, 24 hours a day. Behind the drill head, a robotic assembly line instantly installs precast concrete segments to seal the tunnel. This is a non-stop 170-kilometer marathon of engineering, where the finish line is a new era for humanity. While the spine bores deep below, the surface teams are executing the most complex vertical lift in history. Each residential module is a prefabricated block weighing over 2,000 tons, built in off-site automated factories. These modules are shipped via heavy-lift modular transporters and slotted into the steel chassis like massive Lego bricks. The tolerance for error is practically zero. A 3mm misalignment at the base becomes a meter at the summit. To ensure absolute precision, engineers use real-time digital twinning, syncing every physical bolt to a virtual model. High-altitude gantry cranes, custom designed for NEOM, operate in wind speeds that would shut down any other site. They use gyro-stabilized cables to prevent the 2,000-ton modules from swaying like pendulums in the desert gusts. Every lift is a high-stakes dance between gravity and the relentless, scouring winds of the Red Sea. Once a module is locked, the assembly engineers engage high-energy plasma welding to fuse it to the core. This creates a monolithic structure that behaves as a single organism, distributing stress across the entire wall. But how do you power a 170-kilometer skyscraper without a traditional vulnerable power grid? The answer is solar skin, a photovoltaic coating integrated directly into the millions of glass panels. Every square inch of the city's facade is a generator, capturing the brutal energy of the Arabian sun. This energy is then stored in massive subterranean liquid metal batteries, designed to last for centuries.
This facility represents the height of industrial output, processing millions of tons of raw steel annually.
But in the heart of the desert, power is secondary to the ultimate currency of life: water. The line requires a staggering 500,000 cubic meters of fresh water every single day to sustain its ecosystem. To meet this demand, engineers have built a gargantuan desalination complex at the Red Sea terminus. This facility utilizes advanced reverse osmosis (ARO), powered entirely by the city's solar skin. Massive high-pressure pumps force seawater through nanomembranes at 70 bars of pressure. The brine byproduct is not dumped back into the sea. It is processed for valuable minerals like lithium. Every drop of water within the line is tracked by a smart water AI grid to prevent leakage. Gray water is 100% recycled to feed the vertical forests that line the city's interior atria. These atria aren't just for aesthetics, they are biological air scrubbers, creating a unique microclimate. Assembly engineers are currently installing the zero-gravity irrigation pipes throughout the structure. These carbon nanotube pipes are ultra-lightweight and capable of moving water 500 meters vertically. The sheer weight of the water column is managed by intermediate, pressure-braking reservoirs. This complex plumbing is the circulatory system of a megastructure that refuses to die. But even as the interior flourishes, the exterior faces the brutal reality of desert erosion. Sand is a silent, abrasive, capable of stripping the mirror facade if not for a specialized coating. At 500 meters high, the wind is no longer a breeze. It is a relentless, structural battering ram. The line acts like a 170-kilometer sail, catching the full force of the Red Sea's gale winds. To prevent the entire wall from vibrating into collapse, engineers utilize aerodynamic mitigation. The glass panels are not flat. They are micro-angled to break wind vortices and reduce drag. This brings us to a crucial checkpoint: the sheer endurance of the mirror facade under pressure. Every panel is held by dynamic fasteners that allow for 3 degrees of freedom during high winds. Assembly engineers use ultrasound sensors to monitor the tension in these fasteners in real time. A single loose bolt at this height could trigger a catastrophic zipper effect across the facade. But the glass isn't just strong, it's smart. It uses electrochromic layers to tint automatically. By modulating light, the city controls its internal temperature, reducing the load on the cooling lung. Behind the glass, the secondary steel frame provides the ribcage for the city's internal organs. Logistics drones fly non-stop between the ground and the upper tiers, delivering precision components. These drones are the white blood cells of the construction site, keeping the assembly line moving. Even as we speak, thousands of sensors are feeding data into the city's central AI, the cognitive core. This AI predicts structural fatigue before it happens, adjusting the building's tensioners dynamically. Beneath the mirrors, the city's heart beats in the dark. This is the spine, the multi-level logistical basement. At level -1, a fleet of thousands of autonomous service robots manages the distribution of every single parcel. There are no roads here, no cars, only high-speed magnetic tracks and AI-governed delivery pods. Level -2 houses the high-speed rail, where trains travel at 500 kilometers per hour in a partial vacuum. Building this subterranean artery required removing over 100 million cubic meters of granite and sand. Assembly engineers are currently reinforcing the tunnel vaults with carbon fiber-infused shotcrete. The vibration from a 500 kilometers per hour train is immense. The rails are mounted on active dampening cradles. These cradles use electromagnetic levitation to isolate the city's foundations from the train's kinetic energy. Above the rails, a dedicated level for industrial metabolism handles 100% waste-to-energy conversion. Vacuum tubes pull waste from residential modules at 60 miles per hour, delivering it to the processing core. Every scrap of metal, plastic, and organic matter is sorted by hyperspectral AI cameras in milliseconds. The heat generated by this process is recaptured to drive steam turbines, feeding the city's power grid. This isn't just a basement, it's a giant, underground engine room that makes surface life possible. Managing this complexity requires quantum logistics algorithms that predict demand before it exists. Every assembly engineer on site is linked to this grid, receiving real-time updates on their augmented displays. We are now entering the final phase of the first 4-kilometer module, the proof of concept for the entire line. Critics call it a mirage, but for the 25,000 engineers on site, it is a daily industrial miracle. Every joint successfully welded, every pile driven into the bedrock, brings us closer to an urban revolution. The line is not just a building. It is a declaration that the era of car-centric horizontal sprawl is over. As the final mirror panels of the first sector are locked into place, we witness a new horizon. The cost is staggering, yes. $1.5 trillion is a number that defies human comprehension. But the knowledge gained in material science, AI logistics, and renewable energy is priceless. The techniques developed here in Tabuk are already being exported to solve urban crises worldwide. We have learned how to build upwards, efficiently, and in total harmony with a lethal environment. This is the great leap forward for 21st century engineering, a testament to human ambition. Whether the line reaches its full 170-kilometer glory or remains a monumental prototype, everything has changed. We have proven that we can design, build, and sustain life where life was never meant to exist. The desert has been conquered, not by force, but by the relentless precision of the human mind. Saudi Arabia's Mirror City is no longer a dream. It is a massive, steel and glass reality.